Okay, good morning. Welcome to the 1UP Applied Mathematics webinar series. Um, uh, we're just going to wait probably for another minute or two so we can have other guests in this Zoom webinar. But for those watching on YouTube, please stand by and we're going to start. Thank you. Okay, good morning again. Let's start. And again, welcome to the 1UP Applied Mathematics webinar series. This is actually a weekly series by applied mathematicians all over the whole UP system. And without further introduction, may we call Dr. Aurelio de los Reyes to introduce our speaker today. Hi, Sir Au.
Hello, good morning. Good morning, everyone. Welcome to this 1UP Applied Math webinar series. Our speaker this morning is Dr. Bryan S. Hernandez. He defended his PhD dissertation last December, and he completed the program within 3 years. So his talk is actually a part of his dissertation, and it is entitled Positive Equilibria and Fundamental Decompositions of Power Law Kinetic Systems. Ryan?
Thank you, Sir Au and Sir Jomar. First of all, I'm going to introduce this preliminaries chemical reaction network, or simply CRN. So you have a triple of 3 sets of sets. You have script C, script S, script C, and script R. These are all non-empty and finite sets. So script S, script C, and script R are the set of species, complexes, and reactions with cardinality N, N, and R respectively. We associate, we note that R is a subset of C cross C, and we associate the element AB, the ordered paired AB, to the familiar notation A follow B, or A yields B. The first property is that we avoid loops, and then the second property is that for each A in the set of complexes, there is another complex such that one of them is a reactant and the other is a product in a given reaction. Let's consider the following example. Consider the reaction 2H2 plus O2 will give 2H2O. So this summarizes the combustion of hydrogen gas. So hydrogen reacts with oxygen from the air to form water vapor. So in general, we can write the given reaction to 2A plus E to 2C. So this is the example. For this particular example, the set of species is, so the species are A, B, and C. So this is the set of species. And then for the complex, so a complex is either a product or a reactant. So this is the reactant 2A plus E, while this one is the product 2C. So these are the complexes, the reactant and the product. And for the reaction, there is a single reaction, so this is the set of reactions. We can actually associate A to be 1, 0, 0, B to be 0, 1, 0, and C to be 0, 0, 1. So we can actually write the complexes in terms of linear combinations of these vectors. And these vectors are actually the standard basis for our cube. Each complex can be seen as a linear combination of these elements of the standard basis for R to the n. In this particular case, m is equal to 3. There are 3 species. We now go to these matrices. The first one is Molecularity Matrix, so it's denoted by Y. So it's M by N matrix. Again, M is the number of species, and N is the number of complexes. So for each particular complex, that corresponds to a column. So the entries are the stoichiometric coefficients of the species. And then for the incidence matrix, the notation is I sub A, so it's N by R. So it's indexed by the complexes and the reactions. Now, for a given reaction, -1 is the entry if the complex is a reactant, 1 if the complex is a product, and 0 otherwise. The stoichiometric matrix is denoted by capital M, and this is the product of the molecularity matrix and the incidence matrix. A reaction vector is just for a particular reaction, you're going to get the difference between the product and the reactant. So that would be the reaction vector for a particular reaction. And then the stoichiometric subspace is a linear subspace of R to the n, given by the linear span over R of the reaction vectors. The rank of the network is the dimension of the stoichiometric subspace, which happens to be the rank of the stoichiometric matrix. Two vectors in R to the n are stoichiometrically compatible if the difference is an element of S, capital S, the stoichiometric subspace. We now go to this example. So in this example, you have 5 reactions. The first reaction is x1 to 2x2. The second one is 2x2 to x1. The third reaction is x1 plus x3 to x2. And then the fourth one is x2 decomposes to x1, x3. And then the final reaction, the fifth reaction, x2 to x3. So this is the molecularity matrix. Again, for the molecularity matrix, so it's indexed by the species and then the complexes. So these are the complexes. Of course, the species are x1, x2, and x3. And then for the complexes, you have x1 to x2. So these are the corresponding complexes. x1 plus x3, x2, and x3. So for a particular complex, say x1, this is x1, we just get the stoichiometric coefficients. So you have 1, 0, 0, and then for the second complex, 2x2, so you have 0, 2, 0. And then you're going to do that for all the complexes. And then for I sub A, it's the incidence matrix. So for a given reaction, you're going to write -1 if the corresponding complex is a reactant, 1 if the corresponding complex is a product, 0 otherwise. Now for the first reaction, x1 to 2x2. So x1 is, of course, for the first reaction, it's a reactant, so it's -1. And then for 2x2, it's a product, so it's the entry is 1 and the rest is 0. And then you're going to do that for each reaction. For the stoichiometric matrix, so it's the product of this molecularity matrix and this incidence matrix. And the rank of the network is 3. Now, CRNs can be seen as graphs. Complexes are vertices and reactions are edges. So for example, you have A to B, the reaction A yields B. So A and B are the complexes, which can be seen as vertices. And then the reaction is to the edges. Connected. So 2 complexes are connected if there is a path between 2 vertices. Connected components, so any 2 vertices of a subgraph are connected. Linkage classes, so these are precisely the connected components. I will not define formally what are weakly reversible reactions. So I will just describe them. So the first one, the first reaction is a weakly reversible reaction. For a weakly reversible reaction, any two pair of complexes, there is a path from one to the other, and then you can go back to the other one. So for example, you have A and B plus C. You can actually have a path from A to B plus C, and then you can go back via this path. And then this is another weakly reversible CRN. And this is also another weakly reversible. This is a reversible CRN, and reversible CRNs are also weakly reversible. We have this notation for linkage classes, it's L. And then this is an important concept in CRN. The formula for deficiency is denoted by delta. So you have N minus L minus S. Again, N is the number of complexes, L is the number of linkage classes, and S is the rank of the network. We have the kinetics. So for a given CRN, so you have a CRN, and then for each reaction, you're going to assign a rate function. So that would be a kinetics. Then when you have a CRN endowed by the kinetics, we have a chemical kinetics. Species formation rate function, SFRF. So you're going to get the reaction vectors, and then each reaction vector is multiplied to corresponding kinetics. And then if you get the sum, you have this SFRF. And the ODE of a CKS is dx over dt. So time derivative, so it's f of x. Equilibrium or steady state, so it's a zero of f. A CRN is said to admit multiple equilibria if there is a positive rate, if there exists positive rate constants, such that this ODE system admits more than one stoichiometrically compatible equilibrium. A kinetics K is a power law of kinetics if you have the following form. So the IF entry of the kinetics, so it's K sub I, this is the rate constant, times this powers of x sub j. The K sub i's are non-negative, positive real numbers, while the entries of F are real numbers. So kinetics is defined by a rate vector and this matrix, the kinetic order matrix. Now, if the entries of F are precisely the stoichiometric coefficients, then you have the mass action kinetic set. Let's consider the following example. So this is the example earlier. So you have 5 reactions. So suppose this is F, the kinetic order matrix. And then we actually got a while ago times, we actually got this N. So this is the stoichiometric matrix. So this is the stoichiometric matrix. And then this is the corresponding kinetics. If we multiply, then we're going to get f of x, and this is precisely the ODE for the system. Now, if we equate this to 0, or multiple equilibrium. We now go to this concept, the Biochemical Systems Theory, or BST. BST was proposed by Savage in the late 1960s. He identified that power law representation is a valid description of processes in biochemistry, and the representation combined with generality and simplicity, and this turned out to be rich enough to capture typical nonlinearities. It was used successfully in a number of biochemical and biological applications in past decades, in particular in the 1970s and 1980s. We now go to MSA, or the multistationality algorithm. I will not discuss all the steps. I will just describe how this algorithm can be used to analyze multistationality in the biochemical systems theory. It determines whether a power law kinetic system has the capacity for multiple equilibria for particular rate constants. So you have a CRN, and the CRN is endowed with the kinetic, in particular power law kinetics, and then you have the power law kinetic systems. And then we're going to identify whether that system admits multiple equilibria or multistationality. We're going to the multistationality of a global carbon cycle model with climate engineering by Hecatan. So this is actually the model. So you actually have these boxes, and these boxes correspond to the species. So you have A1, A2, and so on until A5. So you have these boxes are they actually have interactions with each other. Now, for this particular scenario, this if you see a solid line, so that corresponds to a mass transfer, and then for the dashed line, it's actually a regulation. Now, the corresponding CRN, let's just take, for example, this particular interaction. So A2 to A3. So you have a mass transfer. So atmospheric carbon is being transferred to marine carbon. So A2 to A3. So this corresponds to this reaction. And then let's consider the one with the dashed line. So in particular, you have A1 to A2. So this is a regulation. So you're going to see that both in the reactant and the product. So you're going to have A1 plus A2 to A2 plus A2, or you have this reaction A2. So A1 plus A2 to A2. So this is the corresponding reaction for that interaction. So a while ago, we said that the system is composed of a CRN and a kinetics. So you actually have this particular matrix for the kinetic order values. And then multistationality in global climate implies that there may exist tipping points beyond which a return to the original state may be difficult or be prolonged. By showing that multistationality in global climate model may exist, therefore makes the search for tipping point relevant. So this is the relevance of multistationality in global climate. Now, after a series of steps, you actually have 14 steps. So I will not go into details. Now, you have a non-linear system of differential equations, and that will be transformed to this linear system. And this system actually has a non-zero solution called mu. This is a vector for each species, A1, A2, until A5. So since this has a non-zero solution, then the corresponding system, kinetic system, has a capacity for multiple equilibria or multistationality. These are the corresponding equilibria. So this is the first equilibrium, and then this one is the other equilibrium. So we actually have a system, and then you're going to apply the multistationality algorithm for you to determine whether that particular system has the capacity for multistationality. This is actually in the format of the generalized mass action system. We now go to the decomposition theory. The decomposition, we have the following definition. A decomposition of a network N is a set of subnetworks N1, N2, up to Nk of that network induced by partitioning the reactions, the set of reactions. For the corresponding stoichiometric subspace, so the stoichiometric subspace can be written as the sum of the stoichiometric subspaces of the subnetworks. Another definition, a network decomposition N in the following form. So it's the union of the subnetwork. So it's said to be independent if its stoichiometric subspace is a direct sum of the stoichiometric subspaces of the subnetworks. So you have the following concepts. The first one is decomposition. So decomposition is induced by partitioning the set of reactions. And then that decomposition is independent if of the whole network is equal to the direct sum of the stoichiometric subspaces of the subnet. Definition, so incidence independent. A decomposition is incidence independent if the incidence matrix is the direct sum of the corresponding incidence matrices of the subnetworks. By independent, if it is both independent and incidence independent. This is a formulation of showing incidence independence. So you actually have to compute for n minus L of the whole network, and then you're going to compute n minus L for each of the subnetworks, and you're going to get the sum. If the sum is equal to n minus L of that of the whole network, then the decomposition is incidence independent. So this is another way of showing incidence independence for decomposition. We now go to this decomposition theory by Feinberg. So you suppose you have a partition of a CRN, and you have a kinetics for that network, and n is written in the following manner. And you have this E plus Ni Ki, so these are the set of equilibria of the sets of equilibria of the subnetworks, of the subsystems rather. So you actually have the intersection of the equilibria of the subnetworks is a subset of the equilibria of the whole network. Now, this is very important. If the network decomposition is independent, then this is equality. So how do you use decomposition theorem? You can actually analyze the subsystems, and then if the particular decomposition of the CRN is independent, then you can actually use this latter part of the theorem. Another definition, so a subset O of R is said to be an orientation if for every reaction Y to Y prime in the set of reactions, either that reaction is in the orientation, this must be O in the orientation, or its reverse reaction is in the orientation, but not both. For an orientation O, we define this linear map L sub the orientation, so that would be R sub O to the stoichiometric subspace. So we have the following. We are interested with the kernel of this map. As we can see, this is somehow reminds us of the SFRF of the system. Now, suppose we have a basis for the kernel, and you write the matrix representation of the kernel. If you have the idea here is that you're going to partition the reactions in the orientation into equivalence classes. And two elements of the orientation are in the same equivalence class if the corresponding row is equal or actually a scalar multiple of the other. And then the corresponding decomposition is called a P decomposition. Let's consider, so this is a subnetwork of Schmidt's carbon. These are the reactions for this network. And then you can actually choose an orientation. So a while ago, we said that an orientation is, if you have a reversible reaction, then you will get one of them. You will not include both, but you will choose one of them. So in this particular case, for the orientation, we choose R3. No, R this is a reversible reaction, R1 to R1 and R2. So we just choose R1. And then this is the corresponding orientation. And the basis for O is the following. Now, the first row corresponds to R1, R3, R4, R5, until R8. So we can actually partition the orientation, which is a subset of the set of our reactions, R, into two equivalence classes. So there are two equivalence classes. The first one is composed of R1, R2, R3, and R4. And then the second class contains R5, R6, R7, and R8. And then we now go to fundamental classes. So if you have, a while ago, we just got the equivalence classes. And then for the fundamental classes, you just consider the reverse reactions. So if you have a reaction, then its reversible pair is belonging to the same fundamental class. So that would be how we get the fundamental classes. We can easily see that the orientation O is partitioned into equivalence classes, while reaction set R is partitioned into fundamental classes. We have the following definition for the fundamental decomposition, or simply F decomposition, of a network. So it is a decomposition generated by partitioning R into fundamental classes. So in our example, again, we have R1, R2, R1, R3, R4 as the elements of the first equivalence class. And for the second equivalence class, we have R5, R6, R7, and R8. Now, how about R2? So since R1 and R2 are reversible pairs, then they must belong to the same fundamental class. And hence, the first fundamental class consists of elements R1, R2, R3, and R4. And then the next fundamental class contains R5, R6, R7, and R8. We now go to this following lemma by Haisha G. She was a student of Feinberg. Feinberg is one of the main key persons in CRNT. We have this network, so it's a CRN, and always an orientation. And then, if you have the P decomposition, which was mentioned a while ago, then the corresponding subnetworks will have deficiency, either, as you can see, 0 or 1. So that's the good thing for the P decomposition. It partitions the orientation into subnetworks, and each subnetwork has deficiency, which are low. It's either 0 or 1. We will denote the subnetwork classes in the lemma as type 1, type 2, type 3 for items 1, 2, and 3, respectively. So we have the P subnetworks via the P decomposition. We have this F subnetwork. So it is of type 1, 2, or 3 if it contains P subnetwork of types 1, 2, or 3, respectively. This is very important. The deficiency of a subnetwork, of each subnetwork, remains the same. This is because if you have a P decomposition, then if you shift to the F decomposition, then you're going to get the same deficiency with respect to the subnetworks. We have the following definition: an F decomposition is said to be of type 1, type 2, type 3 if it contains type 1, type 2, type 3 subnetworks. Okay. We had some technical difficulty. Okay. We now go to this deficiency 0 and deficiency 1 theorem. Now, a while ago, we noted that under the P decomposition, you have subnetworks of deficiency either 0 or 1. So there are deficiency 0 and deficiency 1 theorems. So we're going to consider these theorems. So this is just a part of the deficiency 0 theorem. Of course, a CRN has deficiency 0. So the statement holds. If the network is weakly reversible, then for any mass action kinetics, regardless of the positive values of the rate constants, the resulting differential equations have the following properties. There exists within each positive stoichiometric compatibility precisely one equilibrium. That equilibrium is asymptotically stable and no non-trivial cyclic composition trajectory along all species concentrations are positive. But we are interested at this point into the number of equilibria. And then this is the deficiency 1 theorem. Consider the following, consider a mass action system. And then the following must be satisfied. So if the network is weakly reversible, then for any mass action kinetics, the differential equation of the system admit precisely one equilibrium in each positive stoichiometric compatibility. Yes. We now go to the following theorem. The following family of CRNs has bi-independent type 3 F decomposition such that the n sub i's are precisely the fundamental classes under the decomposition N with a possibly broken chain of long monomolecular directed cycles of length greater than or equal to 3. Okay, so each subnetwork has length greater than or equal to 3. And the two consecutive subnetworks have at most one common vertex. Now, we have this as an example for illustrating how we can use Feinberg decomposition theorem and the results for the fundamental decomposition for analyzing the multistationality for a particular system. For a CRN with a possible with possibly broken chain of long monomolecular directed cycles of length greater than or equal to 3. This was the figure a while ago. Then, endowed with mass action kinetics, this network does not have the capacity for multistationality. So let's recall the Feinberg decomposition theorem. So you have a partition of a CRN and a kinetics K. So if you have the subnet, the decomposition is fundamental decomposition in particular. You have several decompositions such as linkage class decompositions and so on. So for in this particular case, you're dealing with the fundamental decomposition. You have this particular set of equilibria for each subnetwork. Then we have the following conclusion. The set of equilibria of each subnetwork, if you get the intersection, so that is equal to the set of equilibria of the whole network if the decomposition is independent. Now, we said a while ago that this decomposition is independent, the fundamental decomposition is independent. And then you can actually use the Feinberg decomposition theorem. And we use the deficiency 0 theorem. The deficiency of each subnetwork is 0. So by combining the results on the deficiency 0 theorem and the Feinberg decomposition theorem, we can say that this system does not have the capacity for multistationality. This is our research. The first one is the extension of the results to poly-PL kinetic systems. So what are poly-PL kinetics? These are systems where kinetics are linear combinations of power law. So we have results on power law, and this is extended to results to poly-PL, which is again a linear combination of the power law kinetic systems, where the scalars are, of course, non-negative, which we target to submit by the 3rd week of July. We also have this current research, positive equilibria of Hill-type kinetic systems. So how about this system? So these are systems wherein the corresponding kinetics are rational functions. And the numerator is actually power law, the numerator of the Hill-type kinetic systems. And this has something to do with enzyme kinetics, which we tend to submit by September. So I want to summarize my talk. The first part is to use the multistationality algorithm for power law kinetic systems, for us to use this in the biochemical systems theory, or BST, which we illustrated in particular to the global carbon cycle model of Heck et al. And we show that that model and the corresponding differential equations does not admit multistationality or multiple steady states. And in the second one, we have the decomposition. We show that this decomposition, in particular the fundamental decomposition, can be used to analyze multistationality via the results on the Feinberg decomposition theory, which relates the set of positive equilibria of the parent network to its subnetworks, and also the lower deficiency theorems. So you have deficiency 0 and deficiency 1, and we know a while ago that under the P decomposition and the F decomposition, the fundamental decomposition, the corresponding subnetworks has only 1 or 0 as the deficiency. So you can actually use these results to analyze multistationality of power law kinetic systems. And then these are being extended to poly-PL and rational functions, which are needed in which are exhibited in the Hill-type kinetic systems. So these are the main references. So this ends my talk.
Okay, thank you very much, Brian. And we can go now to the Q&A, open forum. But before that, may we request everyone here in the Zoom meeting to open your camera. Okay lang ba? Hindi si Sir Au hindi daw ma-open yung kanya. Yung iba dyan, edits, Dilan.
Parang hindi din kaya, sir.
Okay, sige.
Hello.
Edits, turn on your camera.
Wag na.
Wag
Dito
din,
ako sa
sige.
kusina.
Sige, okay lang.
Hindi ako mag-turn on ng camera.
You can start the question, kung may question kayo kay Brian, Edit, Sir Au, Dilan. Of course, Sir Au ay advisor ni Brian. Pero pwede ka rin magtanong pa rin, Sir Au, para mas maliwanagan ang mga nanonood.
Hello. Nagsawa na ata sa akin si Brian sa kakatanong ko eh. Anyway, na-summarize niya naman yung main contribution dun sa area eh. parang gusto ko lang ipa-re-emphasize kay Bryan kung bakit importante sa isang network na malaman na merong multi-stability. At though nabanggit niya yon, meron siyang examples para lang maintindihan kung bakit kailangan ng ibang algorithm para ma-determine yung multi-stationarity ng system at ano yung kahalagahan nito dun sa network. So, Bryan, pwede mo bang bigyan ng siguro one or two more statements to emphasize and to clarify yung ginawa mo? So from that chemical reaction network, you want to determine multi-stationarity, pero yung current current na algorithm ay hanggang anong deficiency lang, at ano yung nako-cover nung yung work mo.
Okay. Actually, the algorithm, yung algorithm po ay actually extension siya from the work of G and Feinberg. So, consider nila mass action, but then this was extended to power law kinetics to cover a larger class of kinetics. And actually, may mga nag-exist pong ibang mga criteria for multistationality dun lang sa CRNs. Meron kasing time na sa CRNs pa lang makikita mo na yung kung may multistationality or hindi, regardless of the kinetics. Dito sa ating work, ang ginawa ay you have a network endowed with kinetics, and these are being used to analyze multistationality. And regarding the deficiency, ang deficiency actually, meron, yun nga kanina, pinakita natin na merong deficiency 1 at saka deficiency 0 theorems. How about the CRNs with higher deficiency? So ito yung ating concern. Yung work nila, G at Feinberg na higher deficiency algorithm, kaya siya higher deficiency algorithm, kino-cover niya yung CRNs with higher deficiency. And we extended that to power law kinetics. And then, in-illustrate natin na talagang na-apply natin siya into biochemical systems theory. Dito, ang pinakita ko lang ay yung application niya sa global carbon cycle model. Pero a number of processes ay gumagamit din itong algorithm. Pwedeng gamitin yung algorithm.
May question ako, Bryan. Definitely, we know na yung CRNP is, ang goal niya talaga is to work with parameterless systems, networks. Is there a way somehow, kasi we're talking about multistationarity, no? Is there a way somehow to even approximate the basin of attraction of each of the equilibrium, kung gaano yung size ng kanyang basin of attraction, if meron na bang ganon? Or purely just knowing meron or walang multistationarity, ilan ang equilibrium?
Okay. Regarding po doon, meron actually global conjecture theory by Creasure. I think it's by Creasure. Regarding stability, meron ding mga results, pero ito ay for CRNs, yung mga nakita ko. Pero yung mga nakita kong results ay for CRNs na about stability, persistence, and so on. Regarding the conjecture, hindi ko pa actually na masyadong na-focus yung yung part na yun.
Okay, Brian. Dylan, may question ka, di ba?
Sige na. Sir, ano yung ano? So what are the differences nung result nung ginawa nyo? Kasi naalala ko kay Sir Noel, deficiency 1 algorithm. Ano din siya, multistationality din siya, tapos in-apply din sa carbon cycle model. So ano yung pagkakaiba? I-follow up ko lang yung question ni Sir Au. Doon kay Sir Noel.
Actually, yung kay Noel Fortune ang ginawa niya, multistationality algorithm din, but for deficiency 1 theorem. Kasi masyadong yung deficiency 0 theorem, marami siyang sinasabi. Pero yung deficiency 1 theorem, napaka-konti yung sinasabi niya kumpara sa deficiency 0 theorem. So kaya nagkaroon ng deficiency 1 theorem. Actually, merong deficiency 1 theorem si Feinberg for mass action, tapos in-extend yun ni Noel Fortune. Tapos itong higher deficiency algorithm, mas malawak siya. Actually, tinawag lang siyang higher deficiency algorithm yung KG for mass action kinetics. Pero nag-a-apply siya sa kahit anong deficiency. Ang may nag-exist na previous results on the deficiency 0 and deficiency 1 networks. Pero actually, nag-work siya sa kahit anong deficiency. Kahit 0 or 1 and the higher deficiency. So yun, ang focus ni Noel ay deficiency 1, pero yun, in-extend natin using the results of G.N. Feinberg para ma-extend siya from the mass action kinetics to power law.
Kahit anong power law, sir? Ano yung RDK, NDK?
Yeah.
Okay, thank you, Dylan. Ma'am Edith, may ano ka ba? Question?
Sorry kasi mukha akong dugyot. Medyo marami ng results sa power law kinetic systems, no? Pero hindi natin unlike merong mga CRN toolbox, yung very friendly sa users para may apply natin doon sa ating mga results. Meron ding mga Dylan yun? Control, ano?
Yes, ma'am.
Oo. Pwede kaya nating pero yung CRN toolbox kasi natatandaan ko, hindi maibigay ni na Feinberg yung code para ma-edit natin at ipasok yung mga bagong results natin. So ano kaya ang magandang paraan, Brian?
Actually, yung kala Feinberg po, yun nga po, tinanong ko dati si Ma'am Angie. Hindi nga daw po, para kasi daw po magulo yata yung code nila, kaya daw po hindi.
Ayaw ibigay ni na Feinberg. Pero nagka-communicate naman dati ang natatandaan ko yung kauna-unahan pa naming unang-unang mga papers. Kaya lang hindi siya ma-edit hindi maibigay kasi nga raw magulo. So ano kaya ang magandang paraan kasi ang dami na nating results on power law kinetics no? Na sana readily usable na pag-input mo nung iyong CRNs assuming power law kinetics, ang dali na madali para sa users na kung meron silang mga ganong klase ng CRNs or system.
Actually, tiningnan ko po yung ginagamit, yung pinanggawa dun sa
control.
Control. Ano po siya?
Pinapanteya.
.NET po siya. .NET na nagiging user-friendly. So, baka po pwedeng magkaroon po ng collaboration with some computer scientists for us to develop that kind of
sana kasi ang dami ng results no, and that will summarize the yung sa properties para sa Power law kinetics. Though, hindi ko rin, Dilan, what can you say?
Mahirap.
Ang parang pinagpo-program ngayon si Sir Lauro.
Si Sir Lauro ba ang pinagpo-program ngayon?
Parang may nanghiram siya ng code dati. Ewan ko baka nagpa-program siya sa dissertation niya.
Pero I think po yan, MATLAB.
Oo.
MATLAB. Pero maganda nga po yung itsura ng ng CRN toolbox na
Oo, maganda yung CRN toolbox.
Yung .NET na user-friendly po, pipindutin mo, meron ng results.
Oo. Maganda sana kung makuha talaga natin yung nun maayos no?
Opo.
To incorporate all our results. But anyway, anong direction niyang ginagawa mo? Ano pang what's next to your
Ngayon po kina-consider namin extension nitong PLK as ayun po yung sa poly-PL. Poly-PL na may combination of power law. Tapos pati po yung Hill type. Din po. Hill type rational function, yung numerator po ay power law.
Oo.
Yun po yung, sa ngayon po, gano'n. Tapos yun po, titingnan po natin. Pero I think, kung kaya yung program, I think, kailangan po natin humingi ng tulong sa mga computer scientists.
Oo. Okay. Sige. Okay na ako.
Salamat po.
Okay, thank you, Ma'am Edith. Meron pa bang gustong magpahabol ng question? Si Ma'am Kayan pala ay nanonood sa YouTube. Ayan.
Sir, may pala.
Ay, sige, go Dylan.
Sir Bry, may-apply niyo yung result 'di ba sa sa carbon cycle model ni Smith. Nung napansin ko dati dun sa carbon cycle model, parang kaya natin siyang dynamically equivalent siya dun sa isang deficiency network na weakly reversible. Magko-contradict ba yung dahil dynamically equivalent siya sa isang deficiency zero network, meron siyang positive equilibrium. So that based from previous result. So magko-contradict ba yon doon sa multistationality result nyo ngayon na pinapakita? Or
Actually dapat hindi, 'di ba? Pero maganda sigurong exercise 'yun na i-verify talaga siya. Yeah, maganda exercise siya. Kasi yun nga nagbago yung deficiency. Pero actually sa yun nga sa yung kay Noel na deficiency 1 theorem. Actually, yung deficiency 1 theorem, in-apply ko din yung yung extension ng MSA ng PLK for higher deficiency. Nagtugma siya. Oo, yung deficiency 1 at saka yung higher deficiency. So, nagtugma siya. Yung concern mo ay sa deficiency 0 na naging dynamically equivalent. Sa deficiency 1. Siguro, dapat nga hindi siya mag-iiba, pero I think maganda siyang gawing exercise niya para talagang i-verify.
Baka yung compute ko mali.
Bakit? Ano nangyari?
Hindi, na-observe ko kasi dynamically equivalent na siya dun sa deficiency 0, tapos weakly reversible. So meron siyang positive equilibrium, unique sa bawat stoichiometric classes, parang ganon. Tinitingnan ko baka mag-contradict dun sa mga result natin. Wala. Check ko na lang din.
Yeah, i-check na lang natin. Para, i-check na lang din natin. Thanks for, i-check natin. I-check ko rin. Salamat.
Okay, may iba pa bang questions? Okay, sige. I think okay na tayo, no? Sige. So, ang magko-closing daw si Ma'am Edith. Pero before yon, Sir Au, do you have additional, kahit ano lang, nandito ba si Sir Au? Kung meron kang gustong sabihin dun sa mga gustong mag-work with CRNT before tayo mag-closing ni Ma'am Edith.
Yeah, I think we have a lot of experts now working on CRNT. Nandiyan si Ma'am Edith, si Doc Bryan, si Dilan, si Noel, si Angie Lau, si Ma'am Kayen. So we are inviting and actually encouraging some others who are really interested in this area We have experts who can really help you. There's a lot of things that needs to be done, I guess. And sa nakikita ko, from mass action to power law, and si Bryan, tinitingnan yung poly-PL at Hill type. So na-incorporate na yung lahat ng, hindi naman lahat, pero at least we are gearing towards unraveling some important networks considering non-linearities in the system. So yeah, so for those who are interested, you are welcome to be a part of CRNT family. And of course, Doc Ed is always there, willing to help us. Yeah, thanks, Bryan, for the talk.
Okay, thank you, sir. Now, may we call Dr. Edita si Jose na hindi nga niya lang ma-open yung camera kasi magulo daw ang kusina niya. Okay. Ma'am Edits.
Yes, thank you so much to our speaker for today, Dr. Bryan Hernandez, and our host always, Dr. Rabahante. And Ma'am Kayan sent me a message kasi hindi siya makapasok sa Zoom. So sabi niya, she just want to add that UPD is looking forward to welcoming Bryan as a faculty member. And she wants to invite researchers to explore CRNT to add sa pool of knowledge na contributed by Filipinos. Hindi naman na, I just want also to share to you that one of the NAS outstanding paper awardee is the paper on CRNT. I think we can share the paper with you. It was published in Philippine Journal of Science. Actually, it summarized the past 4 years of results in CRNT. And also, as a matter of fact, Dr. Baltasar Aguda, who is the late Dr. Baltasar Aguda, first used CRNT in his dissertation, but it was in the stoichiometric network approach, or SNA. So stoichiometric network analysis approach. So ginagawa na pala ng mga Filipinos before pa yung CRNT, but without knowing. And then after several years, 2015, we were able to connect CRNT with biochemical systems theory. So it started it all. So after 5 years, I think we have at around 30 published articles with Filipinos as co-authors. So of course it is of course, it is pioneered by Dr. Eduardo Mendoza. So he started it all, no? Okay, so again, thank you so much, Dr. Rabahante and our speaker, Dr. Hernandez, for this session, and looking forward to more talks like this. So, ayun. Sir Jomar? The next speaker will be?
Okay, thank you very much, Ma'am Edits. Next week, abangan po natin yung susunod na speaker. Inayos lang yung actual dates. But ang magiging speaker natin ay from UP Mindanao. Okay, so thank you very much, and magandang umaga ulit, and sana po tuloy-tuloy na ang ating pag-unlad sa applied mathematics community, and stay safe and healthy kahit may pandemic. Thank you very much. Magandang umaga or magandang tanghali na rin. Bye-bye.
Bye-bye.
Thank you. Bye.
Thank you.
Salamat, Sir Bry. Sir Ao, thank you.
Bye.
Thank you, Bryan.